Testing, testing. I got my notification. Testing. Okay. Yeah. Okay. Stop. Lay down. Now is not the time. Okay. Let me just save my attendance again. Record attendance. All right. I'll check attendance again in about 8 minutes, 7.5 minutes. All right. So welcome, gentlemen. Let me see. Points that we need to kind of mention. We're rapidly approaching the end of the semester, right? We have about 4 full weeks before the final, right? So we basically the month of April. I know we have exam 2 somewhere in there. Like when we finish chapter 4, we'll be at exam 2. I think that's like in week 13. The calendar is on the syllabus, but you know we have the next 4 weeks to kind of get everything in order. So with all assignments that are on Pearson, right? You still have access to them. You still get unlimited attempts. It's still only a 10% late penalty. I just want to kind of remind everybody of the hard deadline of May 1st. It should be that May 1st, which should be a Sunday night at 11:59 p.m. going into Monday morning. That's at the top of the week of the finals, right? So once we start the month of May and we move into that week of finals, everything on Pearson is going to lock out. So my recommendation, the order of priority, you want to prioritize any exam that's on Pearson, you want to prioritize that first. You want to get that in order, unlimited attempts, you know, we can work on it, you know, just ask me questions in class, we can talk about certain things. But that's going to be the bulk of your grade. I think about 80% of the grade, I forget the grading rationale, but it's about 80%. It's most of your grade of the exams. And then the homework and quizzes might be like 7 or 8% each, something like that. Almost 10%, something like that. So the homework, you might notice it might be a lot of work for a little bit of points. The homework is really there to just kind of get you ready for the exams, right? Okay. You have support, you have the tutors, you have me, you know, we can work on this stuff. Because I know it gets a little bit funky, right? Sometimes. So just do the best you can and ask for help. I can't think of anything else. As usual, if you have questions, comments, or concerns, feel free to unmute yourself to get my attention and we can talk about it. And let's go ahead and continue where we left off. So last time we started chapter 4 of integration. And today we're going to be looking at section 4.2 on antiderivatives as areas. So the last section, we introduced antiderivatives. It was basically like the reverse of differentiation. So we take the derivative, and with the derivative being the slope of the tangent line at a point. So now we're exploring how to work backwards, given a derivative, how to undo it, and then what does this mean, right? So we have section 4.2, antiderivatives as area. A couple of objectives. We like to find the area under a graph and use it to solve real world problems. And we like to use rectangles to approximate the area under a graph, okay? So in this first example, it says a vehicle travels 50 miles an hour for 2 hours. How far has the vehicle traveled? So with this one, so they want us to, let me see. I'm just going to do a rough sketch. I'm not going to want here. Let's do it like this. I feel like it's a little bit extra. I'm gonna just do a rough sketch. So So basically, they want us to look at it like a chart, right? Where it says 50 miles per hour for 2 hours. So on one axis, we have our, I guess, our speed or whatever in miles per hour. We say v of t, or velocity, and the units are going to be miles per hour, right? We'll just call this our v-axis. And then the other axis is our time in what? Hours. In hours, all right? Those are the units. Okay. Let's see. So if it's going 50 miles an hour for 2 hours, so then, like, for instance, if we said this was 1, this was 2, and say this was 50, right? So then it's basically doing this, right? The velocity staying constant, so they're traveling the same speed for 2 hours, right? And again, we're going for like 2 hours, so that means we're focused here. And let's just make that like a, well, this is fine, right? So the region in question, so what, 50 miles an hour times 2 hours, right? So then basically what we're actually describing is the area of this curve. Let me the area under this curve. Style, let's do like this. So we can just fill it with like this color. That's fine. All right. So if you just like, listen, how far we want the distance, right? So then if we did 50 miles per hour for 2 hours, so basically the 50 times the 2, so 50 times 2 is 100, right? But then if we were looking at this rectangle, that's basically the length times the width, the 50 times the 2. So then that's going to give us 100 miles, which is basically the area under this curve, right? So this one was just 100 miles, but it was from the area under the curve. Because if we said the 50 times the 2, that gives us 100, right? Let's see how the text articulates. So here's the image that we had. You know, the velocity in miles per hour. So they're traveling at a constant velocity. So it's the speed isn't changing. It's staying a steady 50 miles per hour for the whole time, and they're traveling for 2 hours, right? So then it's 100 miles. So what we got. We said we treat the vehicle's velocity as a function, right? That's what we got here. So the velocity was 50, it remained constant the whole time. So there was a flat horizontal line. We graph this function and then we sketch a vertical line at x equals 2, and we get this rectangle, right? Because we're only considering from the time as the time goes from 0 to 2 hours. So this rectangle measures 2 units horizontally and 50 units vertically. So the area is the distance the vehicle has traveled. So 2 hours times 50 miles an hour was 100 miles, right? Let's do another one. Let's just do another one. So in this example, it says the velocity of a moving object is given by this function, right? So 3x, the diagonal line, where x is in hours and v is in miles per hour. Use geometry to find the area under the graph, which is the distance the object has traveled, right? Let me add a page, right? So this is similar, just a different shape. Add a page. Okay, looks like we need to go out to 5. And we're graphing basically 3x. Yeah, I can use some graph paper. Actually, I prefer this one. And tools, proper. So then it's a similar setup as the one from before. So this will be our velocity, and this one will be our what? Time. This will be our velocity in miles per hour, and this will be our time in hours. Okay. And it says that the velocity of a moving object is given by the function 3x, right? So we put t, this x, I mean, So then 3x, and we want to look at it between basically 0 to 5. So let's go 1, 2, 3, 4. Maybe we can go a little bit more. We'll let that be 1. We'll let this be 1, 2, 3, 4, and 5. Okay. Those are hours. And then the velocity. So like for instance, 5 times 6 is 15. Let's go up to like 20. Let's see if we go 2, 4, 6, 8, 10, 12, 14, 16, 16, we got 18. I think 18 is far enough, right? So this was our origin. We said this was 2 miles per hour, 4, 6, 8, 10, 12, 14, 16, 18. I think that's far enough, right? So then for part A, let's see the velocity. It says find the area under the graph, which is the distance of the object that's traveled from 0 to 3, and then from between 3 and 5. So for instance, when x is 3, I think the speed is, come on, 3 times 3 is what, 9? So when x is 3, we go up to 9. My device is like kind of bugging. We go up to 9. It's here. Right, and then I think another one is when x is 5, we go up to like 15. 5, 8, right there. Okay. And so the graph y equal the 3x is here. Let me see. I think we could finish. No. Yeah, let's just do this. Right. This is v of x equals 3x. All right. Yeah, 3. Okay. Okay. So then it says, where'd it go? Use geometry to find the area under the graph for the first 3 hours and in between 3 and 5, right? So we basically have two scenarios because we want to find the area under this first part and then under the second part, right? So we can honestly just use geometry, right? So if we look at the first triangle, like this one, okay, where the base, this is 3, the height is 9, right? And this is a 90-degree angle. So then the area of this triangle is going to be what? 1/2 the base times the height. 27, so 13.5 miles, right? So again, the area under the curve, given the velocity, we basically graph a velocity function, and on the x-axis we have time in hours. Then the area under the curve is giving us the distance, right? So we're just kind of noticing that right now. We're just noticing that the area under the curve is giving us the distance traveled. Okay. And then for the second triangle, we want from 3 to 5. So we can find the area of the larger triangle and subtract the distance that we just found, right? So the larger triangle is this guy. from here to here to here. This one, this one, this one. I'll check the attendance momentarily. Just barely have enough space. I'm going to shrink it. I'm going to shrink it down just a little bit. I am distorting it, but we can still fill in, you know. So the base there is 5, right? The height, 5 times 3 is what, 15. So then the area, we'll call this triangle 1, right? And so then the area of the second triangle is going to be what? 1/2 the base times the height. 50 plus 25 is 75, 35, 36, 37, 37.5. 37.5, right? Miles. Oh, wait. That's the area of the bigger triangle. But remember, we want it from 3 to, we didn't want from 0 to 5, we wanted from 3 to 5. So we're going to say this minus, we need to say minus the 13.5 to get the desired region. 7 minus 3 is what? 24 miles. So from 3 to 5, they travel 24 miles. Let's copy, paste. Okay. So let's kind of check our work, see how do we do, let's reassess, and then we'll take a moment to check the attendance again. We'll go with paper. Okay. Done. So we got 13.5 and then 24. Let's see how do we do. So the graph of the velocity function is shown. We see that the region corresponds to the time from 0 to 3 is a triangle with base 3, 8. Do we have the wrong formula? Should be a 9, right? I think they typed 8, but I think they meant to put 9. Okay. So then 13.5, we got the same thing there. So from 0 to 3, they traveled 13.5 miles in the first 3 hours. And then from 3 to 5, it's a trapezoid. Now they did theirs different. Like they broke it into 2 other simple shapes. Notice you have a rectangle and a triangle. I mean, and that's fine. So then 9 and 6, you know, right here. Where's my pen? Here. Right. So we did the larger triangle minus the smaller. We should do the same thing. 18. Wait a minute. Base is 2. 6. That's 15. Okay. Wait a minute. Oh, 9 and 2. Okay. Yeah. So they broke it into smaller shapes that they're aware of, right? They know that this height here is what, 9, right? From the previous. They know that this distance here is 2, and they know this whole thing is 15. So then you can easily find out that that's 6, right? So then you have the components. You can find the area of the triangle, and you can find the area of this rectangle. So that's 18 plus 6. 24, right? I think that's what we got. 24 miles, right? So they get the same thing, they just did it a different way. But it's just using geometry, right? Break it into simple shapes and then finding the areas of shapes that you know and put them together. All right, so the area of the triangle, 1/2 the base sums the height. So then the 6 plus the 18 gives us 24. Added into areas, we get 24. Therefore, the object traveled 24 miles between the 3rd hour and the 5th hour. Okay. Let's see. We usually leave the quick check as an exercise for you. And let me pause right here for a moment and check Zoom really quickly. This is okay. Keep going. So the last 2 examples, the area function, let me see, the last two examples, the area function is an antiderivative of the function that generated the graph, right? Is this always true? So in other words, like, I was kind of hoping they would just say it directly, but so for instance, given your velocity function, right? If you have your v of x, your velocity, The derivative of the velocity gives you the position function, all right? And then, the derivative of the acceleration, let's write it like this. Okay. So if you have your acceleration function, the derivative of your, and let's do this in terms of t, because usually that's how it is. Based on time, right? Velocity based on time gives you the position based on time. The derivative of your acceleration function usually gives you the velocity, right? So when you take the derivative of the velocity, it usually gives you the position. And is that right? Yeah. Yeah. Right. And vice versa. And then when you integrate, am I getting this backwards? I don't think so. I think we're okay. Let's go with it. But that's the gist of it. Hopefully I'm not getting it backwards. I don't know why I'm gonna brain fog. But here, so let's and that's gonna come up. We'll see this. So the last two examples, the area function is an antiderivative, right, of the function that generated the graph. So is the formula for the area under the graph of any function the antiderivative of that function? How do we handle curved graphs for which the area formulas may not be known? We investigate the questions using geometry and a procedure called Riemann sums, right? So we saw the correlation, like if you basically integrate the velocity, yeah, you get your position function. That is the opposite of what I just said, right? I think it is the opposite. I don't know why I'm getting that backwards. But yeah, so we were given the velocity function, we took the integral, and it gave us the position function, right? I don't know how I got that backwards. So let's kind of keep going. So in the following figure, the closed interval from A to B is divided into 4 regions. So we have some function, right? It's some curve, and we break it up into 4 equal parts from A to B, all right? Each having some width delta x, which is b minus a divided by 4. So they took the distance from B to A, broke it up into 4 equal parts, and then so each part has the same distance. The heights of the rectangles are f of x1, so they're taking the heights in the left-hand corner, right? So the heights of the rectangle comes from there, 2, 3, and 4, right? That gives us a height. We can actually take the heights from the middle of the rectangle or from the right hand. It just, it depends on the question. But they kind of give you the same thing. All right, let's keep going. So then the area of the region on the curve is approximately the sum of the areas of the 4 rectangles, right? So if we look at these rectangles, again, the area of a rectangle is what the length times the width. So for instance, this is going to be delta x. This is going to be f of x1. So then this area is going to be delta x times f of x1. This area is going to be delta x times f of x2. Delta x times f of x3, delta x times f of x4. So then if we add all those areas up, we get an approximation for the area under the curve. It's not necessarily a good approximation, but it is an approximation. So we can denote this sum with some summation notation or sigma notation, which uses Greek capital letter sigma or sigma that you see here. So the sum is I goes from 1 to 4 of f of x I times delta x, right? Right, and this is the same thing, it's just positioned in a different place. This is where the sum of the product f of x I times delta x as I goes from 1 to 4. To recover the original expression, we substitute the numbers 1 through 4 successively for I and f of x I times delta x, and write the plus sign between the results, right? So that just means add up your parts. Oh, I thought I had edited that one. I hate when that happens. Okay, let's do this. Let's just copy and paste. And then work here. I just want to suppress I think that's the answer. Copy, paste. Okay. All right, let's work like this. So write the summation notation for this, right? So notice here we have what? 1, 2, 3, 4. We have five things that we're adding together. So if we're going to write summation notation, So we're going to take the sum as I goes from 1 to what, 5? What is it, 2i? For instance, when I is 1, 2 times 1 is 2. When I is 2, 2 times 2 is 4, 2 times 3 is 6, right? So these are basically all 2, 2 times I. Right? I think that's it. And again, this is just read the sum as I goes from 1 to 5. And so what this means, and I'm gonna just write out what it means. For instance, we basically plug in when I is 1, so that's gonna be 2 times 1 plus 2 times 2 plus 2 times 3 plus 2 times 4. And you keep going until you get to 5 plus 2 times 5, right? So that's 2 plus 4 plus 6 plus 8 plus 10, all right? So then our desired result is here. So note that we're adding consecutive values of 2, right? So I think we got that. Let's try another one. Oh, that's a quick check. Let's try here. So we asked to write the summation notation for this. So we're saying this thing, this is the first one, plus the second one, plus the third, until we get to the 19th, right? All right, so we're basically adding these guys up as I goes from 1 to 19 of g of x of I delta x, right? So if you let I be 1 plus when I is 2 plus when I is 3 until you get to 19. I think that's it for that one. Okay, let's try another one. This is it. I goes from 1 to 19, g of x I delta x, right? That's what we got. Okay, let's try another one. Express this without using summation notation. So instead of condensing it into summation notation, now we're going to undo, right? So we're just going to take this. Let me start by getting the copy. As I goes from 1 to 4 of 3 to the power of I, right? So then all we do is let I be 1. So then this is going to be 3 to the power of 1 plus 3 to the power of 2. And we keep going until we get to 4. Plus 3 to the power of 3 plus 3 to the power of 4, right? 3 plus 9 plus 27 plus 81. Let me see, 12, 37, 39, 39, 40, 120. 120. Okay. We are like breezing through this. I'm going to leave this as an exercise. And again, if you want to go back, just stop me, get my attention. Express this without using summation notation. So, okay. So something like this, as I goes from 1 to 30, h of x of I delta x. So let I be 1, so that's going to be h of x of 1 delta x plus h of x2 delta x plus, we use ellipses, which means continue the pattern, plus, and then keep going until you get to 30. H of x 30 times delta x. So we use ellipses, that just means continue the pattern. So let I be 1, plus when I is 2, plus when I is 3, plus until you keep going until you get to when I is 30. Okay. I is 1, I is 2, until you get to I is 30. Okay, consider the graph of this. Consider the graph that you see here, right? Over the interval from 0 to 600. Approximate the area by dividing the interval into 6 subintervals, and then approximate the area by dividing the interval into 12 subintervals. Let me give myself some space for this one. Now notice that this graph, the highest exponent is a 2, right? So it should be a downward facing parabola. We could use college algebra to jump straight to the vertex. We can use calculus to jump straight to the vertex. I kind of want to just do a rough sketch. Let me see, if I use algebra, the x coordinate of the vertex should be what, negative b over 2a. So then it's going to be what, negative 600 over 2 times negative 1. So then that's when x, it looks like x is going to be what, 300. That's the x coordinate of the vertex of this downward facing parabola. Let's see. So x's, it looks like our x's need to go out to maybe like 600. But when x is 300, what's the corresponding y? So 6 times 3, let me see. Hey Siri, what's 600 times 300 minus 300 times 300?
600 times 300 minus 300 times 300 is 90,000.
90,000. So it looks like the corresponding y is 90,000. All right. So let's just give me a sense of my window. So let's go to my paper. Like, if I find it easier to do graphs on the dots. Okay. So then we'll let this be our x-axis. Here's our y-axis. We said the x's need to go what, to 600? Let me see. 1, 2, that's a 1, that's 2, 3, 4, 5, 600. And then 90,000, so 100,000. So let's go by tens. Let me see. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we're going to label this as 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And I want these to be like hundreds of thousands. These are hundreds of thousands. All right, so that's like 100,000, 200,000. No, that's not, that's tens of thousands. So it's like 10,000, 20,000, 30,000. All right. And then these are by hundreds. I mean, I guess we could just write it out, but these are by hundreds. So it should be like 100, 200, 300, 400. Let me just write it out. I'll go with this for now. All right. So we have the vertex. The vertex is what, 390,000. So then over to 300 and up to 90, which is like here. All right. Let me see, when x is what, 200? When x is 200. Hey Siri, what's 600 times 200 minus 200 times 200?
600 times 200 minus 200 times 200 is 80,000.
Right here. And I'm pretty sure this has some symmetry. We can probably use symmetry and verify. I'm just gonna let's do when x is 4. 400. Hey Siri, what's 600 times 400 minus 400 times 400?
600 times 400 minus 400 times 400 is 80,000.
Okay, so I think that's symmetry. My headphones are dying. Let me switch them out real quick. Okay. Let me see. We can go ahead and do 100. Hey Siri, what's 600 times 100 minus 100 times 100?
600 times 100 minus 100 times 100 is 50,000.
And again, we could verify the symmetry. I'm just going to kind of assume it for right now. I think we have this. When x is 0, looks like we're at the origin. So then that means that more than likely when x is 6, we should be at 0 as well. I'm going to verify it real quick. Yeah, 6 times 6 minus 0, right? So we get this. So then we're going to curve. I think it gets much better than that, right? Okay. So consider the graph of this, right? So we have the graph over the interval from 0 to 600. Okay, I feel good about that. Approximate the area by dividing the interval into 6 subintervals. Okay, looks like we're gonna do this twice. So let me copy and paste. So now if we divide this up into 6 subintervals, right? Let's see, we got 1, 2, 3, 4, 5, 6. So it's kind of already divided. Let's do the subdivisions in like orange. So like we have this one. And again, like the way we're doing this, I think it's more so for like instruction purposes. You're not necessarily going to do it this way, but this is just kind of like to drive home a concept. This is why we're doing it this way. Let's paste. Let's paste another one. Then, okay, if we use the same technique that we did before, where we base it on the left corner, right? So then yeah, like that. Copy, paste. And we get this one. Paste. And we have this one. Paste. This one. And one more. Paste. So we're doing this based on the left-hand corner. Copy. Paste. All right. So now we want to find, let's see, 1, 2, 3, 4. Let's see. 1, 2, 3, 4, 5, 6, right? So we want to find the area of the 6. Now, this first one, the left-hand corner is at 0, so that's why it looks kind of different than the others, right? So we want to find the area of each of these rectangles. Let's do this. Let's go style. That needs to be thin. Copy, paste. 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 And paste. Okay, so basically we find the areas of these rectangles. Okay, So now if we look at that first one, so the height of the first one is 0, right? So that first one is basically 0 times the width is what? Is 100. All right. Now the second one, the height is 50,000. And the width is still 100. All right. I think the width for all of them is 100. Plus the next one was 80,000 times 100. The next was 90,000. So then the sum of the areas. Let's see, we had 90,000 times 100. Then I think we got the 80 again times 100. I think we had another 50 times 100. Okay. Let's see. It should be a total of 6 of them. So let me see. Here's the 80. Here is the 50, and I think there should be 6, right? So let's see. We got 1, 2, 3, 4, 5, 6. All right. So if we add these together, let's see. We can add on what? 2 more zeros. 50. 1, 2, 3 plus 2 more. 5 million, right? And that should be what? 8 million, 80, 1, 2, 3 plus 2. It's 8 million, 9 million, 8 million, minus 5 million. Over 9,000. Okay. I think this is good, right? 1, 2, 3, 4, 5, and then the first one was 0. So let's see. Let's see. So this makes 10 plus 16. These make 26, 36, 35. 35 million, right? 35 million. Now let's put this in context of the question. Move into the earpod. You should still be able to hear me. Okay. Now, approximate the area by dividing it into 6 subintervals. We got this. Okay, so the area under the curve we got was 35 million even. Okay, let's go with it and see what happens. Okay. So then now that's if we divide it into 6 subintervals. Let's go back and redo the same thing, but if we divide it into 12 subintervals, all right? So I think we kind of already have the graph ready to go. So we can do something similar. Anybody got a favorite color? Anybody? So you guys still there? Or am I just like doing this for myself?
Green.
What would you say?
Say green.
Green? Okay. Chat. Let me see. Yeah,
It just.
yeah. We could definitely go through some homework. Go ahead.
Oh no, I was just saying green. That's it.
Okay. So let's do one in green. Let's see. So now we can we had our 6 subintervals, right? So we can kind of put those back. Copy, paste. What's the time? We're good on time for now. So I probably could have just copied what I had before, but this is fine. Ooh. Paste. Okay. So let's cut these in half. So we're gonna basically just do another bar, but at the halfway mark of each of these. And this one is not as clean. looks a little bit off. And then we're just going to come back and kind of redo it the way we did before. Okay, that's good enough. Okay, so then now if we base this on the left corner like we did with the previous, so the first one still looks like a 0, but now this guy goes from here to here. That's weird. Like, there we go. Copy. Paste. This one goes from there to there. So we're doing these based on the left corner. If we did them all based on the middle of these rectangles or all based on the right-hand corner, we should still get the same results. I'm trying to do it at least once first. I'll come back and adjust those in just a moment. Okay, let me adjust these other ones. So then, for instance, this one, let's go there, 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 there. Let's copy, paste. And for the piece that is distorts, we're gonna go 1, 2, 3, 4, boom. Style, like that, feel. I mean, that doesn't really matter. Like that. Ooh, that's the wrong one. That's better. All right, so copy. And so basically we've broken it up into 12 subintervals. It's kind of a repeat of what we just did, just with smaller intervals. But it means much more calculations. See, I like to do stuff like this part because this is like the fun part. You can like do a nice picture, make it, you know, just have some fun. You know, without it being so like analytical all the time. You can have a little bit of fun. Insert. You got to find like come up for air. You know what I mean? Let's paste. Okay. So we have these rectangles, whereas these rectangles under the curve based on the left corner, right? We did it based on the left-hand corner of each rectangle. So then if we go to find the area of each, let's see. So for instance, the first one is 0 times, instead of 100, that's what, 50. So 0 times 50. The next one, when x is what, 50? What's the corresponding y? Hey Siri, what's 600 times 50 minus 50 times 50?
600 times 50 minus 50 times 50 is 27,500.
Okay. So there's that one. And then the next one, the width, all the widths are 50. Now the next height is what, 50,000? Okay. 50 times. I kind of want to do a little bit of a shorthand here. Notice that we're multiplying each term by 50. So I just kind of want to factor out that 50, right? I'm just going to do an ellipses. That means continue the pattern. And I just want to write it differently. Instead of writing it out that way, I want to say 50 times. If I factor out 50 from all of those terms, I'm going to be left with 0 plus 27,500 plus 50,000 plus, what was the next one? So there was a 0, 27,500, then 50. So then the next is when X is 1.5 or 150. When X is 150. Hey Siri, what's 600 times 150 minus 150 times 150?
600 times 150 minus 150 times 150 is 67,500.
Okay. So then I think the next one was X was 200 and that one was what, 80? And then 2.5, so 250? 250? Hey Siri, what's 600 times 250 minus 250 times 250?
600 times 250 minus 250 times 250 is 87,500.
I'm gonna continue down on the next line, plus, I think the next one was 90. So that was a 3. And then I think it repeats at that point because it is symmetrical. So that one is 90,000. Then you got an 87. I think we should have a total of 12, right? Let me see. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, right? So then 87,500. Or we could just say, well, I mean, we can just keep going. 500 plus 80,000. 67,500 plus 50,000. 27,500. And I think that's it. All right, we should have a total of 12 of these guys. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay. All right, I'm going to try this one time with Siri. See, can I get all of this in Siri? Okay. Hey Siri, what's 50 times open parentheses 0 plus 27,500 plus 50,000 plus 67,500 plus 80,000 plus 87,500 plus 90,000 plus 87,500 plus 80,000 plus 67,500 plus 50,000 plus 27,500 close parentheses.
The answer is 35,750,000.
Okay. Seems like it worked. 35,750,000. That was an adventure. All right, I think we got it. Notice that it's close to our previous answer. All right. So that has some implications. Let's copy. Okay, that was an adventure. Let's go here. Paper, like this. Done. Okay. 35,750,000. Okay, that was fun. All right, so we can see that one there, and then the previous one here. All right. Okay. So now let's compare to the prepared notes. And see, we only got 10 minutes left in class. Like that's how it goes. But again, I'm still willing to hang out. I know there was a request for homework. We're almost done here. Let's finish this out, and we'll take whatever time we need to go through whatever questions. I feel good. I got energy, so we can keep going. So example 7, we divide 0 to 600 into 6 intervals of size 100, where the xi's range from basically 0 to 500. All right. Yep, that's what we did. Right. When x1 was 0, x6 was 500. I think we got this. The total area you see it in the upper right-hand corner, 35 million. That's what we got. Then, thus the area under the curve is approximately 35 million. All right, so you can see all this stuff like similar to what we did. Okay. Then they divide it into 12, where the change in x or the delta x is 50. Right, that's what we got. So then x1 goes from 0 to 550. I think we did all of those. And then you see it right here, 37,750,000. All right, kind of a repeat what we did. All right. So the section summary. The area under the curve can often be interpreted in a meaningful way. The units of the area are found by multiplying the units in the output variables by the units of the input variables. It's crucial that the units are consistent. Okay. Geometry can be used to find the areas of regions formed by graphs of linear functions. A Riemann sum uses rectangles to approximate the area under the curve. The more rectangles, the better their approximation. So with that last example, notice how the first one we got 35 million, the second one we got 35,750,000, so they were close. So again, right there, that's what I wanted to mention is that the smaller the rectangles in the Riemann sums, the better the approximation, right? And then the definite integral, the integral from a to b of f of x dx is a representation of the exact area under the graph of a continuous function and y equals f of x, where f of x is greater than or equal to 0 over some closed interval ab, right? So what we were doing here with today's presentation, we were using Riemann sums to approximate the area, right? And so we saw that when we got a smaller subinterval, like the more subintervals we took, which made smaller rectangles, the better the approximation. So then what if we push it to the max, right? Instead of doing 6 subintervals, or instead of doing 12 or 24 or 48, instead of doing smaller, like take it to the limit, right? And so that's what we're going to discuss in the next section. If we were to take it to the limit, how can we get essentially an exact area under these curves, right? And that's what integration is. So integration is basically telling us the area. So that where the derivative tells us the slope of the tangent line at a point, the integral is telling us the area under the curves, right? That's what it in a graphical sense. So that's priming us for 4.3, which we'll talk about on Monday. Okay, guys? I think that is enough for 1 week, right? You guys survived, hanging in there strong. I'm proud of you guys. Even if you just in our YouTube family, it's all good. I know this is not easy. I want to reassure you, just keep pushing, just get your assignments submitted, and get whatever support. Come to class, ask questions, take advantage of your resources. You have support. I'm not trying to go hard on nobody. I'm trying to set you up for success, but I can't give it to you. You have to take it, right? Nobody can give you your freedom. It has to be taken with both hands, right? You got to take it. Right. So with that, I know there was a request to go through some homework. Did you use the Ask My Instructor, or what's the story there?
Yeah, I just did.
Okay, let me pull it up.
I kind of have the base of it. I did one before, but I'm trying to see if it's kind of similar.
Let me pull it up. Hang on. So I'll pull it up over here. This one. Okay, I'll do the first one. I just do it in order. I see you sent 2 of them. So can I just copy this link? Copy. Awesome sauce. Cool. We're just gonna we can close all these out. Close all 6 tabs. Gotta make sure I don't have no incriminating evidence. I'm a human like everybody else. So. All right, let's see. My neck, my back. All right, let's see. Let's try this one. Let me check one other thing. Oh, so from this section, okay, cool. And you be on it. You be asking questions for what we talking about that day. I like that. Okay, a juice company has found. Can we zoom in? So how do we? Can we make this a little bit bigger? Okay, you are on. Oh, right here. Too big. Okay, that seems okay. So let's see. So it says a juice company has found that the marginal cost of producing X pints of fresh squeezed orange juice is given by the function below, where C prime of X is in dollars. Approximate the total cost of producing 285 pints of juice using 3 subintervals over this, and the left endpoint of each subinterval, right? So we have this curve. We want to break the distance from 0 to 285 up into 3 subintervals. round the final answer to the nearest cent. Let's say approximate the total cost. Do we need to make a graph? Okay, I'm going to kind of do a rough sketch. So let's get a copy. We can take it from there to here. That looks good. I'm not going to do an exact graph one before. Let's add a page. And if you guys are like able to process this information, and I know you have like, you know, classmates, I need to track them down because they have been MIA, and I'm like, okay, what are you guys doing? Are you like, you still hanging in there? I got to track them down. I'm gonna come looking for them. But you know, hopefully you all are working together. Okay. So let's see. So notice highest exponent is a 2, so it's a U-shaped graph. It looks like it opens upward, right? So we'll have a minimum. A juice company has found that the marginal cost of producing X points is given by this. Approximate the total cost of producing. It would help if we look at the graph, right? Using 3 subintervals from 0 to 285. This is for X is less than 350, right? Okay, let me put this in my graphing calculator. So I'm going to let's start. Let's do another one like this. That's fine. Reload and refresh. Okay, I'm gonna go to my y equals. How many zeros is that? 1, 2, 3, 4, 5. 2, 3, 4, 5, 8 x squared minus 0.004 x plus 3 x y. Now I'm just trying to think of a window. Zoom. Let's see if Zoom Fit does it. Does that do it? U-shaped curve. No. Mm-mm. So it says 0 to 285. Let me see the X values. Okay. So the X minimum, let's just do like something like -2. X max, matter of fact, if we're going from 0 to 350 or 285, let's go to 300. Hey Siri, what's 285 divided by 3?
285 divided by 3 is 95.
95. I guess we can just do those subintervals. So we'll go from 0 to 300. Thank you. Stop. We're gonna go. Let's go by 45s, right? So let's do this one as like -22. I'm just trying to think of an appropriate window. The max we're gonna go up to 300, but we want to go in steps of 45, right? Because we're gonna see the 90, the 180, and the, what did you say, 95? Hey Siri, what's 285 divided by 3?
285 divided by 3 is 95.
So let me see. Let's go by 47.5, right? Because I just want to see those tick marks so we can have a mark where we want it, right? The Y values. Let's go to like -2. It looks like it doesn't go that high, so let's go up to like 4 and let's see what that does. We can go in steps of 1 on the y-axis. All right, let's hit graph and see what it looks like. It's kind of hard to see. Okay, well this might be okay. Okay, so all right, let's look here. So I'm just going to kind of let this be a rough sketch, like this, kind of like this. Let's see. So we want to go from 0 to where 285. I want this to be like 285 out here. We want to break it up into 3 equal parts. So I think we said it was what, 95? So like this is 95. And I think this is like 190. Right. And then, so for instance, let's clear, let's go to variables. Let's calculate, for instance, when x is 0, the answer should be what, 3? Okay. Let's see. So say this was 3 here. So if that's 3, this would be 2, that's a 1. All right, and that's 0. Let's see. So when x is 0, y was 3. When x is 95, we got like 2.69. So we got something about here, right? So this was the point 95, 2.6922, right? We had the first point 0.3, which was here, right? When x is 190, 2.5288, so 2.5, so that's about here. That's what, 190, 5288, okay, and then 285. I'm basically redoing what we just did, just with this different set. So then when x is, that's about 2.5, so still like about here, 285, 5098, okay? So the curve, you know, it kind of looks like this, right? And then so we want to basically evaluate, we got like this subinterval here, we got this one and this one, right? So then like that, and this one is the left right here. These are the rectangles that we're trying to solve for, right? So all we're doing is finding the area of these 3 rectangles and adding them up, all right? So the left, that first rectangle, the width is what, 95. So we're saying 95 times that height was 3. Plus, again, the width is still 95 times the height. That height was 2.6922 plus the width was still 95. And that final height, 3, 285. Wait a minute. 1, 2, 3, 4. We did 3. We did 2.69. The last one should be 2.5. The 2.5, 2.5288. Right? And those are the 3 rectangles. So then we just crunch those numbers and add them up, and that should work. So I'll just do it here. So then it should be 95 times 3 plus 95 times 2.6922 plus 95 times 2.5288. Okay, 8. We get something like this, and then it said, the total cost. I think this is it. The nearest cent is gonna, so $781. Because the nearest cent would be, you'd have to round up by 1. So then that's gonna bump everything up to 781. Okay. So let's try 781 and see if that works. 781 here. Oh, you're doing that thing again. Ooh, 781. Okay. Hopefully it should give you credit for that, you know, If we work it together and we get it right here, I think it gives you credit for it. Let's try to pull up that other one. Did that make sense, or did you have more questions? Oh, you sent another one. That's cool. Let's
Yeah, so
let's
it just
go ahead.
using three random anywhere between 0 and 285, and you plug them in the equation, I believe.
Okay, so let's back up. So okay, so let's back up. We is the blue part okay? That's the curve, right? That's the function or f of x. Is that part okay?
Mm-hmm.
All right. So then now it says that we want to approximate the cost, basically find the area under the curve of producing 285 pints of juice using 3 subintervals. And it says from 0 to 285. So when I did it, I did 0, I did 285, and I knew I broke it into 3 equal parts. Here's the first, here's the second, here's the third. Right? So then what I did, I said 285 divided by 3, and I got 95. So each subinterval had a width of 95. Is that okay?
Mm-hmm.
So this was 95, 95, 95. So then the height, we based it on the left part of the rectangle, right? So if we start here on the left part right here, that height was 3, all right? Here, the left part of this rectangle is here. So that height was this 2.69. We basically, when x was 95, the corresponding y was this 2.692, right? And then the left corner of this third triangle is here. So that height, when x was 190, was 2. We didn't even use this last one. We just didn't use it here. Because I had kind of paused for a second. I was tempted to use it, but I was like, no, we're just using the left corners. All right. So those heights, the first one is there, the second one is there, the third one is there. Okay. So then once we have the height and the width, the area of a rectangle is the length times width. So basically 95 times this height, 95 times this height, 95 times this height. And that's the area of the first rectangle, area of the second rectangle, area of the third. Then we add those up. Okay.
Okay.
Yeah, let's try another one. That was good. Let's copy the link. And so we're still live streaming, by the way. It's cool. I find and I can only imagine what you guys are experiencing, but that's why I try to make myself available, because I could imagine that this would be a challenge by itself. I think this is kind of a repeat. Oh, you want to work this one? This is the same thing, just with more subintervals. You want to work this one?
Can we do the most recent one I sent? I think that was different.
Okay. Let's if you want, we can come back to this. Let me copy this. Copy, because this is a repeat. It's just you're gonna have to do more subintervals.
Mm-hmm.
This is the same procedure, just catch the changes. But if you want to work it, we can. But let's do the latest one. Oof. So it says a record club found that the marginal profit P prime in cents is given by this guy, right? Where X, let's zoom out. Zoom out. Oh, am I pressing? No, that's the right thing. Not control. I'm just trying to get this to zoom out. Close to that. Let's close this. Let me close all of these, see if that fixes it. Close all 4 tabs. Paste and go. It's connected. For some reason, it won't let me zoom out. Hmm. Oh, that's getting worse. Come on. Here, let's do this. Let's just shut that down. Let's go to Safari. Are you connected? Yeah, I don't know why my stuff is being so temperamental. Safari. Paste and go. There we go. I had to reboot Safari. But anyway, it's like that sometimes. Come on. All right, this will do. Okay. So it says a record club has found that the marginal profit P prime in cents is given by this, where X is the number of members currently enrolled in the club. Approximate the total profit when 180 members are enrolled by computing the sum as I goes from 1 to 6 of P prime of X of I, okay, delta X, with delta X being 30, right? So they give us delta X is 30 for each of those cases. So then, for instance, when I is 1, right? So X of 1, let me see. Oh, right. So when X is 1 here, let me get a screenshot. Do another one. Yeah, that looks good. That's way better. Okay, let me get a copy of this. Okay, we're gonna drop it right here, and then we want to take this guy. We're gonna take that and drop it here. Come on. Stop. She always wants attention. Oh, where's my image? Can I change the order? I'm gonna move this to the back, but that's okay. Let's cut. Sorry, I'm just trying to get that other image on top. Paste. Okay, I got one other thing I can do. Give me just a moment. Let's go like this. Come on. Copy, paste. Okay. And now we can take this. That looks good enough. Okay. I'm just gonna do one other thing. I'm gonna just flat this image and just let it be one image altogether. I'm just doing some technical stuff, sorry. So to behave properly. I'm gonna take that and drop it right here. And we are ready to get the party started. Okay. Because the graph, the other graph I felt like wasn't as clear as the larger one. And so I still have all the pieces. Okay. So with this one, sorry about that. It just took a while to get here, but we got there. Stop, cancel. So we have P prime. Oh, it says approximate the total profit when 180 members. So this is, you see the 180 there. By computed sum as I goes from 1 to 6, where the delta x is 30, right? So basically they're asking us, it's basically the same thing. Find the area of each rectangle and add them all up, right? So that first one, for instance, here, let's write this out. So if we're considering sum as I goes from 1 to 6 of P prime xi times delta x, right? So if we expand this out, what this means is P prime of x1 times delta x plus P prime of x2 times delta x. You just keep going until you get to 6, plus P prime of x3 times delta x plus P prime of x4 times delta x plus P prime x5 times delta x plus P prime of x6 times delta x, right? Now, x1 is what, when x is 0? Because they give us the delta x each time, right? So x1 is when x is 0. Okay. So then this should be equal to P prime of 0, and then delta x is 30. Right? So times 30. Plus P prime. So now I want to say x2 should be 30 because we're just adding 30, right? So then x2 should be P prime of 30. And again, the width is always 30. x3 should be what, 60? The width is always 30. And that's the P prime. P prime, what is that? 90 times 30 plus P prime of 120 times 30. Thank you. This is in person. We keep going until we get to 180, right? So then we're gonna have P prime, I think it's 150 times 30, P prime of 180. Let me check something else. A record company is a record club has found that the marginal profit is given by this, where X is the number currently, or approximate the total profit by computing the sum of this. Now let's think about this really quickly. Let me see. When X is 0, 30, 60, 90, 120, 150. Once we hit 150, we're done. 180 is too far over here, right? So we don't need the 180. That's why I stopped, because of the experience that we had when we were going through the notes, right? I think it says 6 subintervals. No, that's 6, right? It should be 6. So there's 1, 2, 3, 4, 5, 6. If we had did the 180, that would have gone too far. Okay, battery's getting low. So then now P prime of 0. So then we basically plug in 0 into the function there. So I'm going to put that in the calculator again. Okay. So we got y equals, let's see, we got 3 zeros, so negative 0.123 times 6, x to the power of 3 plus 0.2 x squared plus 41.5 times x. Okay. Okay, let's quit. And we basically want to crunch each of those numbers. So if I go to my variables, calling on that function, I think when x is 0, the output should be 0. So that first term is 0. I'm just going to we can just put 0 plus. So now when x is 30, so I'm just going to recall that and put in when x is 30. When x is 30, we got this 1408.8. 1408.8, that's still times 30. Plus when x is 60, we got 3080.4. 3080.4 times 30. 60, 90. 4917. 4917.6 times 30. 120. 6823. Point 2 times 30. That was what, the 120, and then the last is the 150. 8700 times 30. Okay. So then we just, crunch all those numbers. I am tempted. I'm gonna use Siri. I'm gonna try it once. Okay. Hey Siri, what's 30 times open parentheses 1408.8 plus 3080.4 plus 4917.6 plus 6823.2 plus 8700 close parentheses.
30 times 1408.8 plus 3080.4 plus 4917.6 plus 6820. 3.2 plus 8,700 is 747,900.
Looks pretty good. Okay. Total profit, 180 members. Let me see. Let me see. A record club has found that the marginal profit in cents is given by this. That's fine. X is the number of members currently enrolled. Approximate the total profit when 180 members are enrolled. Total profit. 740. Okay, that's what we got. I mean, that could be the case. So we got 747,900. Let's submit that, see what that's right. So then here, 747,900, 747,900. Oh, 747,900, 747,900 near a cent. I think that's what we got. Oh, in cents. Find the approximate total cost in dollars onto the nearest cent. It's so many places where we could have made a mistake. It looks like we might be missing that point. Let me see. I think I may have missed some things. Let me pull this out. I want this like over here. Yeah, there. I'm gonna go to my y equals 0.2. Let's see, negative 0006x cubed 0.2x squared 41.5 times x. Delta x is 30. Let's see. 30, 60, 90. Yeah, I feel good with these. Where do we make a mistake? 1 to 6. Okay. Let me get rid of this guy. Hop back over here. 747,900. And let's theory. So I feel like these are okay. 68, 23.2, 49, 17.6. Okay. 30, 80. I can't bring those back. 30, 80. Okay. Let's do when X is 30. $1408.8. Okay. Okay, so maybe we made the mistake with Siri. Let's just try one more time. Let's see if we get the same thing. We're going to say 30 times 1408.8, 3080.4, 4917.6, 6823, 6823.2, 8700. Okay. Oh, we got the same thing. 747,900. 747,900. 1, 2, 3, 4, 5, 6. Yeah, we got the 6 intervals. I think we got that X as well. And X is 0, 0. I want this one. And this needs to be like this. 747,900. The total profit when our enroll is approximately round to the nearest cent. Trying to avoid having to do it over again. X1 is 0, 30, 60, 90. This should be 6 on. We got 6. Okay. Let me see. I'm just gonna look at this answer. Because I can't see anything else that we can do different. And my keyboard is totally on the frets today. Delete. Come on. Oh, I think it's irritating. Yeah, because we're not doing anything different there. Let me just submit it in cents. Okay, what are our units here? Number of members. Oh, our units are wrong. Okay. We're treating this like it's dollars, right? Marginal profits in cents. So that's how many cents it is. So we need to convert it. We just got to convert it to the right units. That's all. For instance, if you had 100 cents, this would be $1. So you move the decimal left by 2. So we just need to truncate those two trailing zeros. If I can get my keyboard to work, come on. I don't even know why it won't let me do it. Okay. I think I Let me make sure this thing is off. Yeah, that's what we just had the units wrong. So what we did, I think, was fine. I just gotta. So I am working on the iPad, and I guess it's not compatible. I think we just got to get rid of those trailing zeros. If I can figure out how to. There it is. Okay. All right. I think that's it. 7,000. Yeah, that's okay. So $7,497. $79. I think that's it. Let's go with that. Right. So we had what we were doing was fine. We did everything correct. It's just that we were treating the answer as if it was already in dollars. We had to convert it from cents to dollars. So to do that, all we did was divide by 100. Right. And I just realized at the very last second, right there, it says that this is all given in cents. All right. So we had the final units wrong. That was an adventure. Okay. But that's how it goes. Like you just gotta keep kind of going back and forth. Fortunately we were able to figure out what we were doing wrong so we didn't have to do it over. But that's what it takes. Like you do what you think is right, you get to it. If it's wrong, then and now we realize, hey, just be sure the units are proper, right? But so that means that everything else we did was fine. Okay, I don't know if you're still there.
Yeah, I'm still here. I
Oh,
just went through it as well.
okay.
Yeah.
So, but I think you go ahead. Yeah, I want to say you should get credit for it because we got it correct. Did you have others? We can look at more.
I think did somebody say something?
For a split second they like popped in and off, but I had to
That's me.
go ahead. Mr. Taylor?
No, I was just saying. I was just here.
Oh yeah. Yeah, so you saw that one though. I mean, again, so basically what we did was correct. The logic and we just had to realize that this was in cents and not dollars. So we had to convert this from cents to dollars. That was the only change. Okay. Right. So again, the idea, you have your curve. And again, so this one was basically the same like we did from 0 to 180. And they wanted to break it into 6 subintervals. They just kind of worded it differently, but it was the same idea. So then you have the 6 subintervals, and then we basically based the height of the rectangle on the left corner, right, for these examples. So for instance, the height of that first rectangle has a height of 0. And then the second one was 30. And then when X was 30, find the corresponding Y. When X was 60, find the corresponding Y, so on and so on. All right. So if you guys want to do more, I'm game. If you feel okay, then we can call it a day. Whatever you guys want to do.
I think I'm okay. Thank you, Professor.
Okay. Yeah.
I had to get going too.
Yeah, no worries. Okay. All right, guys. So until next time, I think you guys are okay. Just try to help as many of your classmates as you can. I got to track these guys down and see if they're okay. Because I know this stuff is kind of tough, but I'll let you go. Take care. Enjoy your weekend. I'll see you on Monday. Okay. And on that note, we're going to end the session here. And from one beautiful mind to another, enjoy the rest of your day. Take care, guys. Peace.